Slide 1. Water, pH, and buffer solutions. Hello everyone and welcome. Today we'll be diving into the crucial roles of water, pH, and buffer solutions in biological systems. Water serves as the site for metabolic reactions, and understanding acidity and basicity is key to understanding these reactions. Let's begin this journey with Dr. Muhammad Shahid Nadeem. Water is truly the elixir of life, covering about 71% of the Earth's surface. It's the mother liquor where life began and makes up over 70% of our body weight. Maintaining the right water level is critical, and our bodies regulate it through intake and excretion. Understanding water's properties is essential because macromolecules and membranes assume their characteristic shape and function in its presence. The water molecule is a V-shaped structure with 2 hydrogen atoms and 1 oxygen atom. Oxygen's high electronegativity makes water polar, leading to hydrogen bonding between molecules. These bonds, though individually weak, collectively give water its unique properties. The dynamic breaking and forming of these bonds are essential for life. While water is generally neutral and stable, it does have a slight tendency to ionize. This ionization produces hydrogen ions, H+, and hydroxide ions, OH. Remember, free protons don't exist in solution. They associate with water to form hydronium ions. The rapid movement of protons between water molecules is known as proton hopping or proton jumping. The ionization constant Keck describes the equilibrium between water and its ions. In pure water, only a tiny fraction of molecules are ionized. This constant helps us quantify the extent of water's ionization and is crucial for understanding pH. By incorporating the concentration of water into the equilibrium constant, we derive the ionic product of water, Kw. This value, 1.0 x 10, 14 M2 at 25 degrees Celsius, is fundamental for understanding the relationship between hydrogen and hydroxide ion concentrations. It's a cornerstone of pH calculations. In pure water, the concentrations of hydrogen and hydroxide ions are equal. Sorensen introduced the pH scale in 1909, a simple, logarithmic way to express hydrogen ion concentration. The pH is calculated as the negative logarithm of the hydrogen ion concentration. For pure water with a hydrogen ion concentration of 1.0 x 10, 7m, the pH is 7. The pH and pOH values are the same at room temperature. The sum of pH and pOH always equals 14, reflecting the inverse relationship between hydrogen and hydroxide ion concentrations. Substances can be categorized into 3 groups based on their effect on hydrogen ion concentration. Acids donate hydrogen ions, decreasing pH. Bases accept hydrogen ions, increasing pH. Salts formed from the neutralization of acids and bases generally don't alter hydrogen ion concentration. Slide 10. When an acid donates a hydrogen ion, what remains is its conjugate base. For example, when hydrochloric acid, HCl, ionizes in water, it forms chloride, Cl, which is the conjugate base of HCl. Understanding conjugate pairs is essential for grasping acid-base chemistry. Conversely, when a base accepts a hydrogen ion, it forms its conjugate acid. For instance, when ammonia, NH3, accepts a proton, it becomes ammonium, NH4+, the conjugate acid of ammonia. These conjugate pairs are always linked in acid-base reactions. The acid dissociation constant Ka quantifies the strength of an acid. The pKa, the negative logarithm of Ka, provides a more convenient scale. The Henderson-Hasselbalch equation relates pH, pKa, and the concentrations of an acid and its conjugate base. Slide 14. The pKa value is the pH at which the concentrations of an acid and its conjugate base are equal. For example, acetic acid has a specific pKa value. This value is crucial because buffering capacity is maximal 1 pH unit above and below the pKa. Buffer solutions resist changes in pH upon addition of small amounts of acid or base. They consist of a weak acid and its conjugate base, or vice versa. Acidic buffer solutions operate in the acidic pH range. Basic buffer solutions, on the other hand, consist of a weak base and its salt, operating above ppH 7. Ammonium hydroxide and ammonium chloride form a common basic buffer. The pKa value of the weak base determines the effective buffering range. That concludes part 1 of our discussion on water, pH, and buffer solutions. Please refer to part 2 for a continuation of this topic. Slide 19. Slide 20. Slide 21.